let me know. Okay, but we're going to jump into it. So we're going to start off with 2.5. This is applications of linear equations and modeling. This is kind of bummed me out. It does have regression in here, regression lines. Don't know if we're going to have time for regression lines, to be honest with you. It's not something you'll be tested upon. Potentially maybe a project in the future, I don't know yet. But we're just going to focus on linear equations and modeling. So our objectives: apply point-slope formula, determine the slopes of parallel and perpendicular lines, and then create linear functions to model data. Okay? So just quick 2 questions for us. Who remembers from your Algebra 2 or Algebra 1 days, what type of relationship do slopes of parallel lines have? What would you say with that? Do you remember? Okay, they're the same. Do we agree with that? Yeah. And then what type of relationship do slopes of perpendicular lines have? Opposite.
And reciprocal.
And reciprocal. Yeah, opposite means positive, negative. Reciprocal means you flip it. Yeah, so we're going to encounter those in this lesson.
So
Here we go.
I'm always tired this period. I gotta stretch.
Start with the definition.
Stretch this way.
The point slope formula for a line is given by the following. Where m is the slope of the line, and x1, y1 is a point on a line. Okay. I'll highlight that. So here it is. That's what we're going to be using. Now, as a recall to last year, this is derived with the slope formula. That's where it comes from. So my slope formula, and how I'm writing this, okay, we're going to so I'm going to derive this real quick. So we're going to let x and y be any point, okay, and then y1 and x1 is a specific point. So if I want to solve this for, well, y and y1, I'm going to multiply both sides by x minus x1. Okay. So these will reduce out. So we get m times x minus x sub 1 equals y minus y sub 1. So there it is. It's just flipped, but that's where the formula comes from. It's just modeling from the slope formula. Let's try an example. Use the point slope formula to find an equation of the line passing through the point negative 3, 4, and having a slope of 1/3. Write the answer in slope intercept 4. Okay, so there we go. First example, just using the formula, can we write an equation of slope intercept 4? So they actually gave us all the information we needed. One of the things you want to do when approaching any problem is decide, what do you need? Okay, so we need a slope and y-intercept, right? If I'm going to create the equation of any line, I need those 2 things. Okay, without it, can't do this. So they gave me a slope already. The slope is 1/3. Okay, now the y-intercept part. Well, they only give me a point, but that's okay. What I can do is plug these 2 items into here, and when I solve for y, I'm going to get my y-intercept, which is great. So you're doing 2 things with 1 equation here. So this, we're going to get to. So we're just gonna put a smiley face there because we are gonna get to you. So here's my equation. Okay. And if you want to label, you can. So this would be my x1, y1. So note that, and let me highlight it over here. This x and y, you'll never substitute any value for it. That's reserved. Okay, that's reserved for any point that's on the line right there. So we don't need that. The x sub 1, y sub 1, that's a specific point that we want it to go through, which is provided for us. Okay, so we get y minus 4 equals 1/3 x minus a negative 3. Guess I can't erase too well. Put all those things on there still. All right, let's distribute. So y minus 4 equals 1/3 x. This will become a positive, so 1/3 times 3 is just 1. Okay, that works out nice. And then my last step is to subtract, or not subtract, add 4, misspoke, and we get a 5. That's our final answer. Now, think about something. Always go back to the problem, like what did you find? Well, we found a line with this slope, and it goes through that point. So if you want to, you can use like a graphing utility to graph it and make sure, does it go through the point -3, 4? And it does. Okay, let's try another example. Use the point slope formula to write the equation of a line through the points -2.54 and 6.517. Okay. Well, unlike the first example, they don't give me a slope. Again, we need these two items, right? The y-intercept will come when we just, put these in and try to solve for y. But the slope part is not given to me. But that's okay, I can find it, right? So let's use these 2 points to find the slope. So m is equal to our delta y over delta x. Remember, that just means the change of y's and change of x's. So the change of y's would be 17 minus 4. Change of x's would be 6.5 minus 2.5. By the way, you could flip these with your first or second point. You're going to get the same conclusion for it. So in the top we get 13, and the bottom we get a 4. And it's okay to have fractions and decimals there. We're so used to having slopes that work out nicely that we forget that that's okay. So we have the slope. Now I'm going to use this formula to find the entire equation, which includes the y-intercept. And it comes down to, what do we do next? Because we have the slope, and I have 2 points. Well, that's perfect. Remember, both of these points work for this line. Ergo, it doesn't matter which one you use to plug it in. It's your choice. I would pick this guy just because the numbers are a little bit smaller. Okay? So this sounds weird, but I'm going to write it down. I'm going to say I choose the point 2.5 and 4. Again, why am I writing that down? Bless you. It's just so that way, if you look at your notes, you know that you chose that point. Well, I kind of chose it for you, didn't I? But still, that's the point we chose. We could have used the other one, no big deal. So we have y minus 4 equals 13 over 4, x minus 2.5. Bless you. Okay. So let's continue. So we're going to go ahead and distribute the 13 over 4. So we get 13 over 4x minus, this would be 32. No, not 32. I think I made a quick error here. 32.5, yeah. Which actually does say 0.5, I just wasn't trusting myself there. Over 4. And last step, add 4 to the other side. So 13 over 4x. Adding 4 to it, so I'll put on this. So common denominator would be 4, so that'd be 16. So, oh, my minus 16.5 over 4. So there's my final answer. Okay. One of the questions I get is, when is it okay to leave it as a fraction? When's it okay to leave it as a decimal, right? Depends on the situation. If you have a word problem or something to apply it to, it might behoove you just to leave it as a decimal, because then it's easier to interpret what slope means, what does the y-intercept mean. If you're just doing this in general, like just create a line and give me that information, it's okay to leave it as a fraction then, all right? So, let's talk about parallel and perpendicular. All right, so parallel lines do not intersect, and they lie in the same plane. That is critical to note that they do lie in the same plane. From geometry, we talk about that a lot. So if I have two lines like this, as long as they have the same slope values, rise and run values, as you've been told in your earlier grades, we're good to go, right? So just kind of a visual showing those two parallel lines have the same rise and same run. By the way, you know what, let's sneak this in here. If you recall, the y-intercepts will differ. Okay, they will hit the y-axis at different spots. So I guess that's good to point out. I mean, I think it's kind of obvious, but still, just to make sure we're on the same page. Okay, perpendicular lines. Okay. So, intersect at a right angle. Okay, so let's go ahead and draw some. So again, my rise and run values for there. We'll do the same thing for this line, for this slope. So M1 would be 3/5 for this guy, M2 is negative 5/5 for the other. Okay, so those two lines intersect at a right angle. Let's list a couple facts off to the side here when it comes to this. Okay. So if the slope of M1 and the slope of M2. By the way, you probably can gather, that's just line 1, line 2. That's what the subscripts mean over there. Okay. Represent the slopes of two non-vertical, because if it's vertical, it's undefined, parallel lines. Then M1 equals M2. Okay? So if they're, as long as they're non-vertical, then the slopes have to be the same. Okay, next little fact. If M1 and M2 represent the slopes of two non-vertical perpendicular lines, then M1 equals negative 1 over M2, or equivocally, M1 multiplied by M2 equals negative 1. So here's the deal with that second point. Okay, when we're first defining perpendicular, this is usually how we define it, that the product of the two slopes is negative 1, okay? In high school, we try to make that a little bit more clearly. If I were to solve for M1, it's just dividing it by M2 to both sides. So this is the part which we already mentioned, the warm-up. So this is our opposite reciprocal part. Okay. another way to describe what's happening here. But typically, when we say perpendicular, we're talking about the product of those is equal to -1. All right, try an example. Write the equation of the line passing through the point to -1 and parallel to the line -2x plus 8y equals 13. Write your answer in slope-intercept form and in standard form. Okay. Sorry about that. I feel bad when I'm writing stuff up there and blocking the view. So we have 2 tasks, slope-intercept form and standard form. So going back to what I said in the first example, we need 2 things. We need a slope and a y-intercept, which, again, the y-intercept kind of takes care of itself when using point-slope formula. Well, I know that it's parallel to this line here. So what I need to do is figure out what is the slope of that line. Then I can use that information to find the slope of my line. So just solve that for y. Okay, so we're going to add 2x over. So we get 8y equals 2x plus 13. And then we'll divide by 8. So we get y equals, I'm going to reduce this to 2/8 to 1/4. Okay? So my line is parallel to this guy's line. So what would the slope of my line have to be then? A fourth, right? We okay with that? So my slope is also a fourth, just to match this guy. Now, once you do that, ignore this guy. You're never going to use it again. The only reason why that's there is to find your slope. Then you're done. Now, let's go back to our line. It has a slope, and we have a point that goes through it. Let's use point-slope formula. Okay? So we're going to use this guy. So I don't have a choice of points. Unlike this guy, I was able to at least pick a point. I'm kind of stuck here, but that's no big deal. So if you want to label this, you can. I think the more organized you are with math problems, the less likely you make a mistake. So that does help at times. We have y minus a -1 equals 1/4, and then x minus 2. So we get y plus 1 now equals 1/4 x minus, I'm going to reduce it in one step there, so that'd be minus 1/2. Then we'll subtract the 1 to the other side. So we get 1/4 x, and that'd be minus 1.5, so minus 3/2. There we go. That is slope-intercept form. The problem is greedy. The problem wants more. It wants standard form as well. Okay. So we did standard form in another lesson. Let's just recap. Standard form is ax plus by equals c. Okay. Where a and b are not both 0. Okay. Here's another fact. Okay. So a, b, and c are integers, and their GCF is 1. That's critical. Man, I cannot spell. Good thing I'm a math teacher. Okay, their GCF is 1. That's important. Now, over here, as you can see, I don't have integers. I'm going to have to mess with that a little bit. And I don't know if the GCF is 1 or not until I get rid of the fractions. So So originally I had this, so y equals 1/4 x minus 3/2. So I gotta put it in this form. We'll subtract the 1/4 to the other side to get x and y together. Now, okay, a and b are not both 0. They have to be integers. The GCF has to be 1. And there's one other, a. Oh, well, it could be equal to 0. We'll keep it that way. It is possible that it's equal to 0. But it has to be positive at least. Okay, that's another criteria there. So here's what I'm going to do. I'm going to wipe this in like one step. I'm going to get rid of the negative and make these all integers. So if you're looking at the 2 and the 4, what's a least common multiple for 2 and 4?
4.
Just 4, right? Okay, so I'm going to multiply both sides by a -4. That way, I can make that positive. So I'm doing it all in one step. So this becomes x minus 4y, and then on this side would be a -6. So this is my standard form. By the way, because it seems ridiculous, like you already have it in this format, why put it in standard form? Well, sometimes, especially with the y-intercept of -1.5, it might be hard to graph it. Here, I can use intercepts. I can plug zeros in. Yes?
What if the 3/2 still be negative?
3/2 still be negative. Oh, it is. Thank you. Yeah, because it's negative up here still. So that would be a +6. Thank you. Appreciate that. So this is easier to plug zeros in, right, for intercepts. So that might be easier to graph than this guy. But again, just trying to get used to either format and knowing like how to use it is pretty important. Okay, I think we're good to go. Let's keep going. Let's try one. So that was a parallel example. Let's do a perpendicular example. So actually, I have space here. Let's do it. So write the equation of the line passing through the point 1,6. And perpendicular to the line defined by y equals -5/2x plus 1. And we're going to do the exact same thing. We're going to write our answer in slope-intercept form and practice standard form. Okay? All right. So, same thing. I need a slope and a y-intercept. Keyword is perpendicular in this problem. So the slope of this line is -5/2. Well, my slope for my line is not going to be the same, right? Because it has to be perpendicular. So what's the slope of my line going to be?
2/5.
2/5? Okay, do you agree with that? So we're shaking our heads? Yeah. So that's my slope. Okay. And again, once we find the slope, that's gone. Okay, there's no other use for that equation. Now we have the point, we have the slope, we're going to plug it into our point slope form and solve it. So let's see, that's going to give me a y minus 6 equals 2/5, and then x minus 1. Okay, so this is going to be y minus 6 equals 2/5 x minus 2/5. A lot of 2/5. So this is going to be y equals 2/5 x minus 2/5 plus 6. Well, I'll put it over here. So this would be y equals 2/5 x, and then same thing. I mean, if I put this over 1, that'd be a 30 plus -2, so it'd be a 28 over 5. Okay. Again, once you leave as a fraction decimal, I mean, here fractions are fine because we're just saying generically, but if it was a word problem or have context, I'd probably do decimals because it's easier to interpret that way. So slope, intercept, form. Now let's talk about standard form. Keeping in mind all the criteria up here for standard form. So my original equation is y equals 2/5 x plus 28/5. Let's get, it doesn't matter the order that you do these things in. I just try to do in the order that I'm seeing it. So I want to get the x and y to one side. Negative 2/5 x plus y equals 28/5. And then if I multiply by 5, I can get rid of the fractions. I'm also going to multiply by a negative 5, because then that makes my x value positive, which is what we want. Okay, you know, why do we want that positive? It's just to help graphing, that's all. Helps with calculation. So then this is going to give me a 2, which, where am I going to write this? We're going to write it up here. So this will be a 2x, and then this will give me a minus 5y, and then these will cancel out, so I just get a negative 28. And the GCF is 1, by the way. The 2, the 5, and the 28 have a GCF of 1, so we're good to go. If it did have, like if this was a 6, then everything would have a factor of 2. So I have to divide everything by 2 to get to my final form that I want for this guy. So because GCF is 1, I don't have to change it, but if it wasn't 1, whatever the GCF is, divide by it for those 3 numbers. Well, I think we got one objective left. We're going to create linear functions and model data. Okay, so let's give it a shot. So creating linear functions to model data. Here's an example. So we have a cell phone plan or a family plan has a monthly price of $89.99 plus $11 for each additional family member added beyond the primary account holder. What's more application than just cell phones, right? We use those all the time now, and I think cell phone plans now are just insane. I think the amount you pay is just not right. I don't think it should be the case for us, but oh well. Okay, part A. We're going to write a linear function to model the monthly cost, which we're going to call C of x, and that's in dollars, of a family plan. Okay, so that's part A. And then part B, we're going to use it, what we find. So we're going to evaluate C of 3, and the most important thing, interpret the meaning. And the context of this problem. Okay. So again, the most important thing is, what does it mean? Because if we don't know that part, then what's the point of even solving? So we have C of x, and let's just go ahead and define what x is. So we're going to let x be the additional family members. We don't know how many. If you have 10 people on this plan, you better have big pockets. That's a lot per month. A lot to keep track of too. So C of X is just what it's gonna cost at the end. Well, the one thing that's not changing is this guy. That's a constant rate. But what does change is this guy. So the 11 is gonna go with my variable, and it is money, so I should write it as such. So it'd be 11.00x plus the constant rate that's not changing, 89.99 a month. Do you guys know what your cell phone plans are like? Did you ever talk to that with your parents? Yeah, it's you should give it a shot. You should ask them like how much you're paying for cell phone a month, because it's, like I said, it's just too much. I really don't understand why we have to do it that much. But next, evaluate C of 3 and interpret it. So what that means is, what if you had 3 members of your family, right, on this plan? So a small family. So that means I'm going to plug 3 into here and simplify. So C of 3 equals $11 times 3 plus the constant rate of 89.99. Okay, so that's $33 plus the 89.99. We get $122.99, which honestly, that's not too bad. Now my family has too many people on the plan. Growing up, we had, I want to say, close to 10 people on a plan. It was a couple hundred a month. I mean, everyone paid their own cell phone plan, but if you look at the total bill, it was just jaw-dropping. It's like, geez Louise. So now we're gonna interpret the meaning. So let's do that. So this means that the monthly cost of a plan with, how many is it? 3? Yeah, 3 family members is $122.99. Okay. Okay. So what I'm going to do, I have 2 more examples left. So we're going to up this just a little bit. So this is just a nice little generic example. But let's talk about cost, revenue, and profit in our next example. So let's break some things down. So first, let's look at some vocab words with it. So when you hear a linear cost function, okay, so this models the cost, which we'll call C of X, to produce X items. Okay, so we have something like C of X equals mx plus b, where m is the variable cost per item. And b is the fixed cost. Okay, so going back to all of our prior examples with the y-intercept is always fixed. It's not going to change. Now, a linear revenue function. Okay, so this models revenue, which we're going to call it R of X. I know, very sly with the naming. For selling X items. You can call these anything you like. You really can. You don't have to call it C of X, R of X, but it makes it easier to know what you're looking at. So that means R of X equals P times X. So the product, PX, represents the price per items P times number of items sold X, okay? So how much did you sell and at what price did you sell them at? So there's your revenue. So you have cost, we have revenue. So then the last one has to be profit, right? We talked about how much it costs to do this, how much we're making. Now let's talk about how much we actually are earning. So we have here a linear profit function. Okay. Models the profit for producing and selling X items. So that'd be like P of X equals our revenue minus the cost. Okay? So there we go. Those are our three that we're going to use in our next example. Now let me ask you this. What if I told you that I broke even? Like I did all this work and at the end of the day I broke even. What does that mean for this context of the problem? Break even point. Did I earn anything if I broke even? No, right? So that means the cost of producing and what I sold equal each other, huh? So if you want, you could just put here, because we're going to see in this example. So if you hear the word break even, okay, so what that means is the revenue equals the cost, okay? I didn't make anything, which is always important for a business, right? Like, when does that happen? Because if it does happen, I need to be making sure I sell a lot more. So here's an example. We have your student council is selling flower bouquets for Mother's Day. Oh, that's very nice. That's sweet. And they're doing it at $10 per bouquet. The cost to set up and reserve the gym is $160. Furthermore, the store, that student council, bought the flowers cost them $6 per bouquet. Okay? So we have a good bit of information here. The student council selling flowers for bouquets for Mother's Day, $10, and the setup reserved for gym is $160, and they bought the flowers for $6 per bouquet. Okay. I think a lot of times, I know in the past, like I've always had people like, I don't know where to start, okay? And first I gotta write the questions down. But highlighting or underlining like key parts can help. So in this problem, I know it costs, or not costs, we sold it for that much. So if you wanna put sold underneath it, okay? This is a cost, because it costs us $160 to do this. Okay, and this is also a cost for us. Okay, it's costing me $6. So not only am I losing $160 for reserving the gym, I'm also losing $6 each time, and I'm only selling it for $10. Okay, so just highlighting or maybe putting some stuff underneath it can help you organize your thoughts. So part A, we're just going to write a linear cost function. Part B, we're going to write a revenue, linear revenue. Function. And then part C, write a linear and there's more, but we'll just stick with those three for right now, okay? So, linear cost, linear revenue, linear profit. Let's just go ahead and create those three based on the information given to us. All right. I'm going to use those names for the functions. So for my cost, C of x, well, let's see. 160 is never changing. That's always going to be that. I don't know how many of these I bought, but they're $6 each time. So it'd be $6 times every bouquet that I buy, plus the 160, which again, that never changes. So there's my cost function right there. My revenue, how much am I making for each one? Well, this is an easy one. I'm selling them for $10 a piece, however many I do sell. So that'd just be R of X equals, sorry, that doesn't look like a zero, does it? $10, okay? So far so good with that? Now, profit. That's when we take how much I made minus how much it cost me overall. Okay, so I'm going to subtract these two. So my profit is going to be the 10x minus the 6x and the 160. Okay, be careful with this because you are subtracting everything here, so that negative has to go to both. So my profit to finish this is going to be $4 minus 160. So that's the equation I want to work with. Now, not done, we got two more parts to this one. I'm going to put it over here. I'm just out of, yeah, I'm out of space. I don't want to squish it. So part D says, how much profit will, I'm going to abbreviate student council, I'll just put SC, make if they sold 30 bouquets. Okay, so how many would they get if they sold 30? Okay, well, we already have our profit, right? I don't have to, and this is the best part, I don't have to plug it into all of these equations to figure it out, then subtract. This profit equation does all of that in one step. So we already did the work for it, let's use it. So P of 30, okay, equals, so it's gonna be 4 times the 30 minus the 160. Well, already, sorry, student council ain't gonna like this one. Negative $40 is what they lost. Ouch. Not good. So in other words, you can figure out ahead of time if that's good or not, right? Which is great, because why not? You have some equations that you can work with, see if it works for you. Okay, so then let me ask this. Let's determine the break-even point. If I can determine that, then I can sit there and decide, oh, they have to at least sell this or more. Well, actually, I should just say more, because I don't want to break even. I want to actually earn some money. Okay, so looking at this, that's when these two are equal to each other, right? When the cost and revenue equal each other, we broke even. We didn't earn nothing. So R of X is the 10, yeah. The cost is the 6 plus 160. Okay. So we'll subtract it over. And hey, this comes out nicely. And we get 40. So that means, and could you figure it out without doing this? You could probably guess just by looking at it that 40 would be the break-even point. So right here, let's interpret it, okay? So I'll say SC needs to sell at least 40 bouquets to, well, yeah, to break even. But I would tell them, hey, sell more than 40 if you want money. If you value your time and value that you want to make some money, sell more. Okay, so last example, and we'll be done. relate a linear model to relate two variables. Now this comes from page 219 in your book, by the way. I'm just going to draw a very quick graph of what this looks like. Very technical what I'm doing up here. Let's see, 30. And 57 to 20. Wow. I'm gonna move my big head out of the way soon. Hold on. Again, what I did is I just summarized it. There we go. So we're talking about blood pressure. Something that as you get older is quite important. When you're younger, not as important. Because you're still healthy. Once you get older, things break down and you need to start, thinking about blood pressure. So it's a bunch of points. The x-axis is an age for years. Your pressure is on the y-axis, and then the 2 points. Those are the critical things right there. Those 2 points I just picked out of there. And what I did is I created a line with those 2 points. I thought these 2 points best represented the data. That was my line of best fit. Not a regression line. A regression line would actually consider all the points. This is just what I thought looked pretty good. So for part A, we're going to use the points, the 30 and 110 and 57 and 135, to write a linear model relating y as a function of x, okay? And again, I chose those 2 points because I thought it worked best. So let's do that. Again, just like the other examples, I need a slope and y-intercept. So the slope part I can do, so I'm going to do the change of y, so 135 minus 110 over 57 minus 30. So we get 25 over 27, which is 0.93. Okay. Now, because I have context, I am going to use a decimal because that's going to be easier to interpret than the fraction itself. Now, using my point slope formula, I'm going to go ahead and use this slope, and then any point I like, because both these points satisfy it. I'm going to pick the 30 and 110 because those are even numbers. Even numbers are easier to work with. So I get y minus 110 equals 0.93, x minus 30. I'll distribute. Okay. And like I said, you could use 57, 135. You're going to get to the same answer. And we're going to add the 110 over. And we get 0.93x plus 82.1. Where's that marker? There it is. Now again, does that represent everything? No, it's just a prediction line that we can use. Not the most accurate prediction line because I picked the 2 points, but it's still a prediction line that we can use. Okay, so part B, interpret the meaning of the slope. Okay. So that's this guy. I want to interpret what that means in the problem. So we're talking about age and pressure when it comes to this. So here's what it means. The slope of 0.93 means that the average increase in diastolic blood pressure for adults is 0.93 per year of age. Okay? So it's just the average increase of it. Because again, I'm just saying that it's projecting along this line here, okay? Not that it's gonna account for every age and year, but it's like a good rough guess for it. Okay, I'm gonna put part C over here. So C, last one. So we're gonna use your model from part A to estimate the pressure for a 60-year-old person. Okay? So you're using our model from part A, which is that equation, right? We're gonna use that equation to help predict for someone that's 60 years old. Okay? So, that's when X is 60. So I'm gonna plug 60 into my equation and see what kind of pressure it gives me afterwards. So I'm gonna rewrite the equation over here. So Y equals 0.93x plus 82.1. Okay, go ahead and make the direct substitution. And that old timer is gonna have a pressure of 137.9. Okay. Now, is that good or bad? Not a doctor, couldn't tell you. Might be good, might be bad, I don't know. But let's go ahead and just write a sentence underneath it. Again, I don't want people in the back. I'm gonna write the explanation up here so you can see it. So what this says is that based on the sample data, the estimated blood pressure for a 60-year-old is 137.9. Okay, so that's what we just projected there. So what did we do? We came up with 3 examples with some applications of how we can create linear models. And the most important thing is just interpreting what our answers mean, especially when it comes to slope. What does the slope mean? Okay, good to go. All right, you guys are awesome.